Hello, it's Stat 134, Lecture 40, the last lecture. Last time we were talking in section 6.4 about the bivariate normal, which we can write some new notation here. We say that UV is bivariate normal with parameters mu U, sigma U, mu V, sigma V, and rho. So we have a theorem we proved last time that the standard bivariate normal has MGF e to the s squared over 2 plus t squared over 2 plus st rho. Today we're going to review the concept test from last time. We'll review MGF and we'll show properties of the bivariate normal using the MGF. So last time we did this concept test. A test score in math and physics is bivariate normal, rho greater than 0. The average is 60 on both tests and the SD are the same. Of students scoring 75 on the math test, we showed that less than half scored over 75 on physics. So one person writes if rho is 1, it would be exactly half. Another writes due to the regression effect, those who scored 75 on math should expect to regress to the mean for physics since both tests are independent. And another student writes the scores of students who scored 75 on math is normal centered on the regression line. 75 is above the regression line, so the proportion of students above 75 is less than 50. So that's what I show in this picture here. So you can look at concentrating on the math students who get a 75. We have a normal distribution centered on the regression line. And those who got more than 75, that percentage is shown in green, and that is less than the area in yellow, which is 50%. So remember, the MGF is the expectation of e to the tx. It has many properties. We can bring the a down to get the MGF of AX of t, and that'll be the same as just the MGF of X of AT. X and Y are independent if and only if the moment generating function of X plus Y is the product of the moment generating functions. We can find the moments of X by taking higher derivatives of the moment generating function and sticking in 0. And also the moment generating function is unique. So for example, if you find the moment generating function is e to the t squared over 2, then you know that x is standard normal. The bivariate MGF is defined as e to the so the expectation of e to the sx plus ty, and it's important to note that you can bring the s and t down. In fact, you can bring the sx plus ty down so that you just have the moment generating function for sx plus ty of 1. And using this, you can show that xy is independent if and only if the bivariate MGF splits as a product of MGFs of x and y. So recall that two random variables x and y are independent. If they are independent, then the covariance is 0, or in particular the correlation is 0. However, the converse is not true in general, right? So correlation being 0 does not imply that x and y are independent. So for example, if x is standard normal and y is x squared, x and y are dependent, but you can show that the covariance of xy is in fact 0. And the reason is that the expectation of xy, which is expectation of x cubed, you can show that that's 0. And you can show that that's 0 using, for example, the third derivative of the MGF of x. And then since the expectation of x is 0, you find that the covariance of xy is 0, and hence the correlation of xy is 0. So So what we see from this is that, so what we see from this is that you can have correlation xy being 0 implies that xy is dependent. So if xy is standard bivariate normal, then the correlation is 0 if and only if x and y are independent. So in this case, when you have xy standard bivariate, you have equality. You have equivalence. So let's see how that's the case. So as I mentioned earlier, the bivariate MGF splits exactly when x and y are independent. And so xy is standard bivariate normal has this MGF we showed last time. And so that splits exactly when rho is 0, because mx of s is e to the s squared over 2, and my of t is e to the t squared over 2. So next, let's recall from lecture 30 that the sum of independent normal random variables is normal, or I should say even a linear combination of independent normal random variables is normal. But what about dependent normal random variables? So it's not always the case. However, we have this theorem, let x and y be standard normal, and the correlation of x and y be rho, then xy is standard bivariate normal if and only if sx plus ty is normal for all constants s and t. So this is a way that you can show that xy is standard bivariate normal if you can show that sx plus ty is normal for all constants s and t. And so the proof of this is pretty straightforward, going in the forward direction. If sx plus ty is if xy is standard bivariate normal, we can write what sx plus ty means by writing y in terms of x and z. And since x and z are IID standard normal, it follows that any linear combination of x and z are normal, and so sx plus ty will be normal. Conversely, if sx plus ty is normal, you can find the expectation and the variance of it, show that the expectation is 0 and the variance is s squared plus t squared plus 2st rho. And so what we want to do is we want to show that xy is standard bivariate normal, and what we're going to do is find its moment generating function for xy, and the moment generating function for xy is exactly e to the s squared over 2 plus t squared over 2 plus st rho, because sx plus ty is normal. And here I'm using the fact that I know what the MGF of a normal is, and I've written it above here in this formula here. So of course rho, mu here is 0, but sigma squared is s squared plus t squared plus 2st rho, and a here is 1. So that follows then that xy is standard bivariate normal. Yay! So we don't need to restrict ourselves to x and y being standard normal. You can show that if uv is bivariate normal, then actually that's equivalent to su plus tv being normal for all constants s and t. And I just put the proof of this at the end of the lecture. It's very straightforward. So then we did a concept test. Let xy be bivariate normal, then 2x plus 3y plus 4 and 6x minus y minus 4 is in fact bivariate normal, because you can check that for any a and b, a times 2x plus 3y plus 4 plus b times 6x minus y minus 4 is normal. And the reason I know that is because when I rearrange things, I have a linear combination of x's and y's, and x and y I know is bivariate normal, so this is going to be normal. And then it just follows from the corollary above. So finally, let M be a student score on the midterm, F is student's score on the final, and let's find the chance that a student scores higher on the final than the midterm. Well, we can write the probability that F is greater than M is the probability that F minus M is greater than 0, and F minus M is normal since MF is bivariate normal, and we can find the expectation and variance of F minus M. We'll show the expectation is -5 and the variance is is 68. So then I'm just finding the probability that a normal -5, 68 random variable is greater than 0, and that is 1 minus phi of 0.61 or 27%. So that's the show, guys. That's Stat 134. We'll start reviewing on Monday. Have a great weekend.